Okay, we have reached the last main concept for rotational motion, and that is angular momentum. So we've been through rotational kinematics, rotational dynamics, rotational kinetic energy, and now we're going to be really in rotational momentum. What is angular momentum? It is the measure of how much rotational motion an object has. In other words, it is the moment of inertia times the angular velocity. If momentum was mass times velocity, rotational momentum or angular momentum will be the rotational equivalent of mass, which is moment of inertia, times the rotational equivalent of velocity, which is angular velocity. The symbol for angular momentum is a capital L. I don't know why. The units for angular momentum are kilograms, meters squared per second. So it's the unit for moment of inertia times the unit for angular velocity. The equation, L equals I omega. So the equation for angular momentum is the same as the non-angular counterpart with P equals mv. We're just dealing with the rotational counterpart. So L equals I omega. Conceptually, there's not much here in terms of what angular momentum is. It's more for when we get into conservation of angular momentum. But just to show you, like say you're given, I should say just a reminder, that R omega equals your linear speed. So omega equals V over R. If we're dealing with a point mass, your moment of inertia equals mr squared. So L could equal, for a point mass, mr squared times V over R, or mrv. If you notice, for a point mass, P equals mv, L equals mrv, so L is equal to linear momentum times the radius. Your formula sheet will not give you this, and this is the more common form that you might see in problems, but you will have this, and you do know that momentum equals mv. So by multiplying the radius by the linear momentum, you can get angular momentum, and again, this is for a point mass. The reason we say point mass is because the moment of inertia is mr squared. If we're dealing with a rod, a sphere, really any other shape object, then it would not be the case where L equals PR. Okay. Angular momentum is conserved when there is no net external torque acting on the system. So just like our linear momentum was conserved when there were no external forces outside of the system, angular momentum is conserved when there's no external torque. And angular momentum being conserved means two things can happen. First, it can be a single object that has a change in moment of inertia or a change in angular velocity. So either I changing or omega changing would give you a change in angular momentum, or you could have a collision, and if you have a collision, then you'll have a change in angular momentum. So, equation. Change in angular momentum means initial moment of inertia times the initial angular velocity equals final moment of inertia times the final angular velocity. I used I's and F's here. Here you can go back to A and B like we did when we were doing conservation of momentum. It really doesn't matter, but this will be subscript heavy. So this would be what you would use. So just I initial, omega initial, I final, omega final for a single object where one of those two things is changing. So unlike linear momentum, change in linear momentum was mass times change in velocity. Mass didn't change. So unlike this case, your change in linear momentum deals with a change in rotational inertia and a change in angular velocity. So your mass itself isn't going to change, but your moment of inertia can, and that will happen if the distribution of the mass or the shape of the object will change. Okay, so this would be for the first case. If you're dealing with multiple rotating objects and you have a collision, then you would say I initial omega initial for object 1 plus I initial omega initial for object 2 plus however many objects you have equals I final omega final for object 1 plus I final omega final for object 2 plus keeps on going. So just like when we had linear momentum, let's say you had two cars that were colliding, you looked at the mass and the velocity of each before and after the collision. It works the same way with angular momentum conservation. You look at the moment of inertia and the angular velocity of each before the collision and the moment of inertia and angular velocity of each after the collision. I believe your formula sheet gives you delta L equaling something along this. I don't have it in front of me right now. But your formula sheet also gives you the rotational equivalent of impulse without really calling it that. So we know from linear motion, and this is going to get confusing, I'm going to write this out, that impulse equals your net force times delta t, which also equals your mass times the change in velocity, which is just, by definition, change in momentum. So impulse, by definition, is change in momentum. Change in angular momentum will equal net torque times time, which will equal change in moment of inertia times change in angular velocity. I believe what your formula sheet gives you is T net equals delta L over delta T. So all this is saying is that a net torque will cause a change in angular momentum, just like a net force caused a change in linear momentum. So this is on the formula sheet just so you can see what that is, how that would be used. I have not seen very many problems using this. Mostly what we're going to be doing are problems with this or this. So let's just get right to the examples. Okay, first, a piece of pizza dough has a mass of 1.5 kilograms. A piece of pizza dough that has a mass of 1.5 kilograms is in the shape of a sphere with a radius of 0.05 meters. The dough is initially spinning in the air at a rate of 15 radians per second. This causes the dough to stretch out into a disk with a radius of 0.15 meters. What is the new speed of the dough? And we're going to ignore any outside torques. So what we have here is a sphere, so pizza dough that's initially spinning, and then it flattens out into a disk, but it's still going to be spinning. Call that A or B or initial and final. If we list our given information, we know that the mass of the dough is 1.5 kilograms. The radius initially, so my initial radius is 0.05 meters. And my initial angular speed is 15 radians per second. It's going to stretch out into the new final radius of 0.15 meters, and we are looking for omega final, so the final angular velocity. Okay, first, moment of inertia for a sphere, so my initial moment of inertia is 2/5 mr squared. My final moment of inertia for a disk is 1/2 mr squared. So this is the first case of conservation of angular momentum where you have the same object but the shape is changing, so moment of inertia and therefore angular velocity change. So change in angular momentum equals I initial omega initial, which equals I final omega final. My I initial would be 2/5 mass times my initial radius squared, omega initial, and that equals 1/2 mass times my final radius squared times omega final. Mass cancels out, it's on both sides. And then my only unknown here is omega final. So 2/5 initial radius squared, omega initial, over 1/2 of my final radius squared equals omega final. Putting in these numbers, we get 2/5 times 0.05 meters squared times 15 radians per second over 1/2 of 0.15 meters squared equals omega final. Multiplying this out, we get 1.33, keeps on going, radians per second. So omega final is about equal to 1 radian per second. Okay, you'll notice that the angular speed decreased by a lot when the pizza flattened out. That's because the larger the moment of inertia, the smaller your angular speed will be, and 1/2 with the larger radius is going to give you a larger moment of inertia than 2/5 of a smaller radius. So in general, small moment of inertia means a higher angular velocity when you're dealing with conservation of momentum. That's why whenever you see a figure skater, if you're watching ice skating, you see a figure skater, they're going to start with their arms out and then they're going to bring them in closer to their body. That's going to increase their velocity so they can spin at a higher rate, but it's going to decrease the radius. That's the same reason when you're orbiting a planet, so this is just kind of a note. But when we were doing Kepler's laws, say you had the sun and then you have a planet in an elliptical orbit, they're going to move faster when they are closest to the sun because the radius is smaller. So for a point mass, moment of inertia equals mr squared, conservation of angular momentum, the mass isn't changing, but the r is. So because as you go around the ellipse, you have a larger radius here, a smaller one here, you're going to have a smaller moment of inertia here and therefore a higher angular velocity. So in terms of Kepler's laws, so I told you it would come back with angular momentum, but the whole reason that planets travel faster when they're closer to the center of the mass is because of conservation of angular momentum. Okay, so that was a little side note. Let's get back to the other examples. I'm going to do one more that you should definitely watch, and I'll do two more if you want to keep on watching after that. But at least watch one more so you can see an example of a collision. A 40-kilogram child is initially at rest on the edge of a merry-go-round. The merry-go-round is a solid cylinder with a mass of 30 kilograms and a radius of 1.5 meters. The child begins walking around the edge of the merry-go-round at a linear speed of 4 meters per second relative to the ground, which causes the merry-go-round to begin rotating. What will the angular speed of the merry-go-round be once the child begins walking? So here we have a merry-go-round. Here's the center, and you have a child standing on the edge of the merry-go-round, and they're both at rest. The child then begins walking. Trying to draw this kind of a top view, but not really. So let's say they're now walking along the edge of the merry-go-round, and it's going to start spinning. Okay, so given information. Mass of the child, I'm just going to call that MC, is 40 kilograms. Initially at rest, so V initial equals 0, means the angular speed is also equal to 0. Merry-go-round, so call that mass M, equals 30 kilograms. Radius of the merry-go-round, I'll call that RM, equals 1.5 meters. The child begins walking around the edge of the merry-go-round at a linear speed. So this is all before. So the final linear speed of the child would be 4 meters per second. And the merry-go-round is going to begin rotating. So we are looking for the angular speed of the merry-go-round. Okay, so this is conservation of angular momentum, but this is where you're going to have two separate objects. So this would be I initial, omega initial for the child, plus I initial, omega initial for the merry-go-round, and that's going to equal I final, omega final for the child, plus I final, omega final for the merry-go-round. That should be a subscript M, not an actual mass. Before the child starts walking, the merry-go-round is at rest, and so is the child. So in the beginning, both of these are 0. So that means that 0 equals I final, omega final for the child, plus I final, omega final for the merry-go-round. So therefore these are equal to each other, just one's negative. So negative I final, omega final of the child equals I final, omega final of the merry-go-round. Running out of room. We don't know what the child's omega final is, but we know that linear speed equals r omega, so V over r equals omega. For the child, they are a point mass, so therefore moment of inertia for the child equals mr squared. And then for the merry-go-round, it's a disk, so that moment of inertia equals 1/2 mr squared. So the only unknown in all of this would actually be omega final for the merry-go-round. So this would be negative mass of the child, r squared, times V over r, that's my omega, over 1/2 mass of the merry-go-round, r squared, and that equals omega final for the merry-go-round. R squared appears in both of those, so that can go away. Negative mass of the child, which is 40 kilograms, times 4 meters per second over 1.5 meters, because he's standing on the edge of the merry-go-round, over 1/2 of 30 kilograms And that's it. Equals omega final. So multiplying this out, we'll get negative 7.11, keeps on going, radians per second for omega final. Notice how the sign of the angular velocity is opposite the sign of the linear velocity for the child. That's because as he starts walking in the way I drew my diagram, so he starts walking this way, it's going to cause the rotation. So I have him moving in a positive direction. It's going to cause the rotation to be clockwise, which would be the negative direction. So whenever you have any object walking on a spinning object, the rotation sign will be different than the linear velocity sign. So coming back down here, it's only asking for angular speed, so it would depend on how you drew your diagram in terms of what that sign would be. Omega final is about equal to 7 radians per second. Okay, if you felt okay with those two examples, then you can stop here. If you want to see more, I'll do 2 more. We have a 3 meter diameter merry-go-round with a mass of 250 kilograms spinning at 20 rotations per minute. John runs around the merry-go-round at 5 meters per second in the same direction that it is turning, and then jumps onto the outer edge. John's mass is 30 kilograms. What is the merry-go-round's angular speed after John jumps on? So what's happening here, we'll do a top view. Here's the merry-go-round. It is spinning. Again, doesn't matter what way it's spinning. And then we have John who's running in the same direction that it's spinning. So that would be my initial before. And then the merry-go-round and John become one when he jumps on, and we want to know what the new angular speed would be. So given 3 meter diameter means that the radius is going to be 1.5 meters. Mass of the merry-go-round is 250 kilograms. Initial angular velocity of the merry-go-round would be 20 RPM. John has a mass. The mass of John is 30 kilograms. And John's initial linear speed, so V initial, is 5 meters per second. And we are looking for omega final, so the final angular velocity once he jumps onto the merry-go-round. So this is again another collision with conservation of angular momentum. So we can say that moment of inertia for the merry-go-round, omega merry-go-round, plus moment of inertia for John, omega John, and these are both initial, equals, I'm going to write this a little bit differently. Once John jumps on the merry-go-round, they are going to have the same angular speed. So it's kind of like an inelastic collision. So this would just be moment of inertia for both of them added together times the final angular speed. Okay, merry-go-round is a disk. John's a point mass. So I for John equals mr squared. I for the merry-go-round equals 1/2 mr squared. Because he is running around the edge of the merry-go-round with a linear speed, he's still running in a circle, so he does initially have an angular velocity. And because of that, we can't cancel anything out. But we'll see once we put the formula for moment of inertia in that things do go away. Okay, so just rearranging this, we have moment of inertia for the merry-go-round, omega merry-go-round, plus, this is initial, plus moment of inertia for John, omega John, initial, over each of their moment of inertias added together equals omega final. Okay, so moment of inertia for the merry-go-round equals 1/2 mass of the merry-go-round, r squared, times omega, plus mass of John, r squared, times omega for John. So remember, omega equals v over r. We know John's linear speed, we know the radius. So this would be times v initial over r over 1/2 r squared plus mj r squared. That equals omega final. R squared appears in every single one of these terms, so it goes away. And cleaning this up a little bit, we get 1/2 mass of the merry-go-round, omega initial, plus mass of John times v initial over r over 1/2 mass of the merry-go-round plus mass of John equals omega final. Okay, my only issue here before I can put any numbers in is the fact that it gave us omega initial in RPM. So we just need to convert that to radians per second. So you would do 20 RPM times 2 pi over 60 seconds. And if you remember, I stored that 2 pi over 60 in my calculator as R, and I would suggest you do the same thing. So whatever this is, so 40 pi divided by 60, that would be what we need to put in for omega initial. Okay, now let's just put the numbers in. So we get 1/2 mass of the merry-go-round, 250 kilograms, times 40 pi divided by 60 radians per second, plus 30 kilograms times 5 meters per second over 1.5 meters over 1/2 of 250 kilograms plus 30 kilograms equals omega final. Okay, so putting all of this in your calculator and hopefully not making a mistake should get you 2.33, keeps on going, radians per second for omega final. So once John jumps on that merry-go-round, it's going to go from 20 RPM to, so 20 RPM, which is actually equal to, let me just put this in real quick, so 2.09 RPM, sorry, radians per second, to 2.33 radians per second. So him jumping on this merry-go-round actually is going to make it spin slightly faster. So my omega final is about equal to 2 radians per second. And it makes sense because he's running around the merry-go-round. He's not initially at rest, so he is adding his angular speed to the angular speed of the merry-go-round, so it's going to make it go faster because they're going in the same direction. What I want to do in the next problem, if you're still watching, is the same exact thing. John is now running in the opposite direction. So we want to see what his what the merry-go-round's angular speed would be after John jumps on if he's running opposite the direction that it's turning. So the only thing really that's going to be different here is the signs. We can still set it up the same exact way. I'm not going to redraw the diagram. But we know that 1/2 m1, so 1/2 mass of the merry-go-round times omega initial plus mass of John times v over r over 1/2 plus mj is going to get us omega final. The only difference here now is that I have to make either this or this negative because it's in the opposite direction. So I'm just going to make the v negative. So instead of a 5, he'll be a negative 5 meters per second. So we get 1/2 times 250 kilograms times, that was the 40 pi divided by 60 radians per second, plus 30 kilograms times negative 5 meters per second over 1.5 meters over half of 250 kilograms plus 30 kilograms equals omega final. This is going to give us 1.04, keeps on going, radians per second for omega final. So it's about 1 radian per second versus 2 radians per second when he was moving in the same direction. So you can see here the fact that he was going in the opposite direction is going to slow down the angular speed of the merry-go-round once he jumps on, because it's essentially taking some angular velocity away. Alright, so if you stayed on for all 4 problems, great. Hopefully you feel pretty good about these, and we'll do some practice in class tomorrow.